So we're going from the very research to the very engineering. So I'm going to talk about RyuJIT. If I say JIT Blue, you can just translate that to RyuJIT because JIT Blue is the old code name. But why RyuJIT? So sort of a nerdy thing. So RyuJIT is a Japanese sea dragon, which I actually knew nothing about. But the idea was that we wanted some tie-in to being a JIT compiler, and the canonical compiler book is also known as the Dragon Book, so that's where the name came from. So I'm going to talk a little bit about the history of the .NET JIT, and then kind of move on to what it was we were trying to achieve with the new JIT, and then kind of go through the structure of the front end and the back end of the JIT, where we are now in the future. It's going to be a pretty quick scan through the whole thing. So back in 1996, before I showed up at Microsoft, x86 was it. It was the only architecture that mattered. The CPU is always getting faster, so really focusing on code quality wasn't all that important. So what we have is a JIT that has decent code quality in a small package. And, you know, decent, not great. In 2001, we needed to have .NET on Itanium. So you can sort of say this is one of the things that, one of the impacts of the Itanium era that survives to this day. So what happened was we're going to use a C++ optimizer because Itanium is pretty hard to JIT for, Itanium, aka i64. And it's really focused on the server. They don't care much about startup time, so it doesn't really matter if it takes you a long time to JIT your methods. But you know, servers have lots of RAM, so it doesn't matter if your compiler is not only slow but also big. So the i64 JIT works, or worked, it probably doesn't anymore, but lots of algorithms that don't lend themselves to JITting. So the next thing that comes along is AMD 64. And again, you know, we're looking at servers, right? So we expect that that'll have characteristics more like Itanium than like x86. So we're going to start from the i64 JIT. And that's where, you know, the Itanium impact is still with us today. So this is the JIT that we're still using for AMD 64. But the thing is that this is no longer a server-only thing. And I'll just take a little aside here because I know there are probably some people out there who you know a little bit about UTC and say, well, you know, at least you're getting really good code quality. But one thing you should know is that in order to actually get that to work as a JIT and not have really unacceptable compile time, basically you had to cripple the UTC backend so that you could get it to run in reasonable time. So now you're paying for this, you know, fairly sophisticated thing that you have, you know, tied its hands behind its back. And, you know, so now we've got 64 bits that we actually care about the JIT time as well as the code quality, neither of which we're really getting what we want from JIT 64. Then in 2010, we need to support ARM. And so this is, you know, in some sense, the target, the characteristics of the target, at least the characteristics of how you want the platform to be deployed, looks more like x86. But the problem is that ARM32 is nothing like x86. So we end up spending a lot of time getting the JIT to work, pretty bad code quality, and not great compile time. So now where are we? So we've got an x86 JIT that's fragile, and I'll talk a little bit more about that later because I think that's a key point. The x64 JIT is, as I said, both messy and slow. We have really bad code quality. We're looking at ARM64, and you know, what are we going to do? So this was the green light for RyuJIT, which, as I say, was previously known as JIT Blue. So what's the vision? We want a high-quality JIT compiler, good throughput, good code quality, good feature and fixed turnaround time, and, you know, mom and apple pie. So we're going to use that vision to drive how we architect this thing. So we want to offer developers a high-quality JIT compiler. So to do that, we really need a modern compiler architecture. We want good throughput, so we really need to have linear or at least near linear algorithms in the compiler. We want code quality, so you know, let's actually advance to at least the 90s in terms of compiler technology, SSA-based optimizations, value numbering, and this is a particular design of value numbering that actually takes advantage of some of the type safety that we can assume in the JIT. And the idea is that we want to have dialable CQ, code quality. And when I say code quality, I didn't understand that term before I arrived at Microsoft. So this is runtime performance. But I've now drunk the Kool-Aid, so I say CQ when I mean runtime performance. But we want to be able to dial that relative to throughput. And the idea is that, you know, eventually we'd like to be able to be more adaptive, and I'll talk about that again later as well. We want to have better feature and fixed turnaround time. So this is where, you know, we're really paying for the existing JIT32 architecture. That it is a very difficult code base to work in. And in order to be able to do anything with any kind of agility, we need to fix some of its drawbacks. We want to have consistent and predictable performance. So we've got a single code base for new features. I'm going to just briefly talk about those. We want to eliminate all of the sort of baked-in x86 isms in the code. And we want to be able to more easily move to new architectures. And so we're going to isolate the architecture-specific things. So given all that, what did we decide to do? Well, we actually still decided to evolve JIT32. And you might say, well, why? Well, I would say, again, I'm probably jumping ahead of myself here, but the biggest motivation is compat. That we don't want to start over and have something that behaves differently in fundamental ways. So we're focusing on areas where we can get real value. We're not going to rewrite stuff just because it would be fun, which it is. We spent a lot of time debating the things that we thought need to be restructured. And there are some things that still exist that I would like to see restructured, but we didn't. We just looked at the things that really were causing us to make bad engineering decisions. And so our first instantiation is on the 64-bit, the x64 JIT. And really, you know, this is something where we've got some existing issues because of the bad, both the bad compile time throughput, but also the mediocre code quality. So again, we're reusing the basic structure of the JIT32 IR. Again, there's some modest architectural trade-offs. There's, like I say, stuff I'd like to have seen us change, but huge risk reduction in both functional compatibility and bug-for-bug compatibility. And that's really a challenge, getting that right. So this also allows us to deliver benefits in phases without having to go dark for a long period of time while we reinvent everything. We've got something we're calling rationalization of the R trees. There was the IR trees. There was some really ugly ways that the trees were structured that made it difficult for the JIT compiler to do things carefully. And so we're phasing in a rationalization of the trees. We've added some more object orientation. This is more about our ability to do good engineering than the end results. And it's pretty much structured like a standard compiler. We've got a high-level tree structure that's mostly equivalent to the IL, IL comes in, we build these trees, and we're moving from what were fairly pattern-based optimizations to more semantic analysis. Then we take that same IR after we've done the front-end optimizations, and we make some modifications so that we have fully exposed all of the platform specifics. And by that I don't mean machine instructions, but I mean instructions from which code can be generated without having to have anything going on implicitly. All right, so what do we keep? We kept the fundamental tree and IR structure. We kept the importation, that's where we read in the IL. We kept the inlining. Again, we're rationalizing the tree representation. There were some problematic nodes, like an assignment was a tree node with an assignment at the top on the left-hand side and the right-hand side, and that just doesn't work all that well for a compiler because the compiler would like to be able to assume that I evaluate the thing at the top after I've evaluated my children. And in assignment, that's not the case. Again, we're restructuring some of these problematic nodes. Question marks and commas were also things that were that sort of broke the assumptions of a conventional compiler and code generator. And we have effectively the same IR in the front end and back end, but the front end is really looking at things as a tree. It does all its traversals in terms of, okay, I'm now looking at the context of an array reference, and let me look at my children. Whereas in the back end, it's really a linear sequence of instructions, because that's how register allocation happens, and that's how code generation happens. And again, the things that are sort of new and different are the introduction of static single assignment and value numbering as the drivers for the optimizations, which really cleans up the way the front end looks. And then a linear scan register allocator and linear code generation. So I have to take a little aside here. I don't know how many of you, have spent any time looking at register allocation or code generation, but the existing JIT had this really odd mix of it would do coloring register allocation on variables up to the first n, and it's not important really, except that it's too small. Up to the first n variables, it would do coloring, and then it would predict the additional registers that the code generation was going to require to actually evaluate the trees. And it was called regpredict, but it could only be conservative. It could never err in terms of not having enough, because there were places where the code generator just couldn't spill. So needless to say, you had these two separate phases that were linked in really bad ways. So that was my least favorite feature of the existing JIT. So what we ended up with is a front end that looked like this. And so what's here in orange is the existing JIT 32. And you'll notice that sort of structurally, it didn't change a lot. You can pretty much, follow this and then follow this, and they look exactly the same. So, except that, what you've got in these boxes, so once we've imported the IL, we've done the inlining, the morphing is just doing some fairly straightforward pattern matching type of transformations on the trees. Loop optimizations, we've gotten a little more clever. Now we do a better job of array bounds check elimination. But then from that point, we do SSA and value numbering, and instead of these lexical optimizations that look for patterns and compare the names of the variables and figure out what has been killed in fairly complex and error-prone ways, instead we have value numbering and SSA analysis that then drive the common sub-expression and other optimizations, assertion propagation as well. So I don't know why I have a future there. I think that's a remaining remnant of a previous slide. We had an interesting development period for a while where we actually had one group working on the front end and a separate group working on the back end. And at this point, after that, it actually went that direction. So I think what I meant to tie in was that there was a time when, from the assertion propagation, we're actually going to the JIT32 backend. And meanwhile, the backend team, oh, whoops, I'm going to go back up to that picture, and then I'll come back. Meanwhile, the backend team was using the JIT front end, going through this rationalization phase and to the new backend. And we sort of just fell into that mode, but it was actually a fairly effective way to not all be stepping on each other's toes at the same time. All right, so what we now have is a static single assignment. I don't know if this is something, I'm assuming that people are mostly familiar with that since this is a language community, but basically this is a form of representation of data flow analysis that allows you to have near linear algorithms for optimization. So we've moved to that. We've got SSA renaming for, and it says they're all local variables and temps. In the interest of near linear performance, we still have constraints on how many variables and temps we will track. And we're working on ways to increase the limit and or remove it, but we still have that limit. We're doing SSA-based copy propagation, and it forms the basis for the value numbering, which then drives all of the optimizations. Value numbering being I assign every expression a value number, and if I then encounter that same value number, I know that those are exactly the same. And so the determination of value number takes into account the kills that happen along the way. This also takes into account knowledge of the behavior of the heap. So for example, if I kill a field of an object, I don't kill its other fields. I only kill that one field. And I guess I've talked through most of this. So that's where we're using field maps that take advantage of the type safety information that we have in the CLI to be able to not make the most conservative assumptions about heap references. And again, for common subexpression elimination, previously we were using lexical equivalence. It's sort of the evolution of the previous JIT actually had it doing some fairly clever things with the lexical CSE, and so there are actually cases that we don't do quite as well today, but we're still working on those. So by lexical, I mean, so I will consider something as being a possible CSA if I have A plus B over here, and I have A plus B here. They are lexically equivalent. But this A may have a different value than this A because I may have, changed the value of A. Yes. But sort of in the optimization literature, there's sort of the notion of lexical versus, I can't even think of the other word that's used. But yeah, so that's what it means. They have the same name. They have the same storage location. But lexical doesn't take into account value equivalence. You have to determine that separately. And again, we've improved the both the loop invariant code motion and array bounds check elimination by basing them on the SSA. So now I'm going to talk a little bit about the back end. And here we have two phases. One phase is called rationalization. I don't know why it keeps chiming at me when I use the laser. It's a little irritating. Sorry about that. So this is where we take nodes that we really would never have designed into the IR and transform them into something that looks more like the IR we'd like to have. We expect that that phase will go away once we are only ever generating rational IR. But this is part of this sort of evolutionary process. But the next pass, which is called lower, is where we take the IR and we don't actually, we're not generating machine, we're not generating, one-for-one correspondence with the target, but we are ensuring that everything that's going to require a register is explicitly represented at that point. So it still looks very much like the incoming IR. An add is an add. It doesn't, you don't need to do anything different to express that, oh, this is an add for x86 or an add for ARM. They're basically just the kind of operations you'd expect to see. But what we do is we ensure that we've got all the register references exposed. Then we go into a linearized register allocator. We used to actually have a path from there to the existing code generator, and that was probably the worst engineering choice I have made in years, because that was just a path of despair. So we abandoned that and said, no, we really do need a new code generator. And really all it is we call it instruction selection, or there's another word we call it, but anyway, encoding. It's only taking these things that we know generate fairly straightforward representations. There's no interaction. If I'm generating this instruction, this tree node, I don't have to look at any other tree nodes except the ones whose results I'm consuming. So it's a very straightforward instruction selection phase, and then we use the same emitter because there's a lot of, just work involved in in producing something that can generate instructions. All right, so basically, I think I said all of this. These are logically atomic, but not necessarily a one-to-one mapping. All that we really require is that register lifetimes are exposed. We do have this weird notion of internal registers because it makes it possible to make the IR much less verbose. So again, I talked about that. The linear scan register allocation is something that's almost just a direct implementation of what's in the literature with some minor tweaks. It still requires a lot of tuning. Register allocation is one of those things that is notorious for being dominated by heuristics that have the sort of whack-a-mole nature. You tune them and this gets better and that gets worse. So there's a lot of tuning remaining to be done. Some things that I thought are really worth mentioning, and I realized later that I had left some out, but I think that there were some really good sort of engineering choices made during the development of this JIT. First of all, it was really convenient that we had a mechanism to fall back to the existing JIT. It was really nice to do this for JIT 64 rather than trying to do this first for, say, ARM 64. Because we're able to just say, oh, this isn't yet implemented, fall back to the other JIT. And so everything just continued to work, and we could gradually add functionality as we built it up. Another thing that has been really handy in terms of ensuring that we can continue to compile the vast quantities of code that this thing is going to actually have to encounter is something called super PMI. And so PMI stands for prepare method invocation or invoke. Anyway, basically what this allows us to do is a record and replay of all the communication that happens between the JIT and the VM, or the execution engine. And so this allows us to very quickly test things, at least in terms of, well, I know when I run all this stuff, I don't get an assert and I don't, crash and burn. And that has been extremely handy. Another thing that is not quite at the ready for prime time point is semantic diffing. And this has a lot of promise because what this gets me, what super PMI gets me is, okay, I know that it's not going to actually error out. But the semantic differ is able to say, I'm not able to prove that the code you were generating before and the code you're generating now are the same. So you'd better go look at this. I think it'll be a little while before we're at the 100%. But when we get to the point where those things are small enough, that that rare enough that when they occur, we can go look at it and convince ourselves, then that will be extremely valuable, because it's very time-consuming to run all of the tests that we have at our disposal. And another thing is stress modes for the registry allocator. We have a lot of stress modes, and they have, I would say there's probably an equal distribution of bugs that have come out of this that are either due to, well, the stress mode was just wrongly implemented, or bugs in the registry allocator, or bugs elsewhere because it exposes corner cases in downstream in the code selection and elsewhere. So the first instantiation of this, as I mentioned, is for x64. We are now at feature parity. So we've released 2 CTPs now. One just went out last week. The first one, we didn't have edit and continue, and we didn't have, what else? Something else. But now we're at feature parity. And we're doing quite a bit better than JIT64 in compilation speed, but more importantly, the outliers are much better. So on average, it's 2x, but yeah, so as much as 40x. So it's still slower than the 32-bit JIT, but considering how much better we are than JIT64, it's not really a concern at the moment. Once we replace x86 JIT, we might have to worry about that. So for the code quality, we are sort of generally better for real-world code. There's some things that we are still trailing on, and there's still work to do. This is based on the second CTP that went out last week. So just by way of explanation, the light blue bar is standard deviation, so anything that falls within that bar is not very interesting. But the stuff that's the big blue bars that are up, that's where we're doing better than JIT64, and the ones that are down are the ones we're still looking at. But it's looking pretty good for now. So what are we working on now? Loop cloning. We've done some work on loop cloning. The idea is that where possible, I can check, is everything within bounds? Well, then just go do this fast version of the loop, and if not, do this other version. And ideally, we'd like to not even put that cloned version of the loop in the code, but just generate it as needed on demand. We're not quite there yet. We're working on support for SIMD, or basically SSE AVX. And the idea is that these are platform agnostic, variable length, and by that I mean variable depending on what platform. Generic vector types. Vector of T is the current name. I'm not sure how it'll end up. It's changed a number of times in the last few months. What was I trying to find? So anyway, there will be some common fixed length types, 2F and 3F, for example. This is actually coming out in April. We're still, like I say, tweaking what the surface area is going to look like, but we've already talked to MVPs, and we're pretty excited about it. We've also talked to Mono, and I'm not sure if any of you are familiar with mono.simd, but they have their own version of these that look a lot like the C++ intrinsics. But they were actually happy to hear that we're working on this, and they don't even like theirs. So they indicated their willingness to adopt. And then ARM64 is going to be next, and a JIT for Project N, which I'm not going to elaborate on. Oh, the graph, okay. Yes. I don't have that slide. It's pretty good. It's mostly, it's a little better than this, but there's still some things we need to work on. So longer term future work, I'd hope to spend a little more time on this, but I'm running out of time. So we're going to spend some time working on dynamic optimizations, and I'll talk a little bit about what I mean by that in the next couple slides. x86, we do not plan to support SIMD, for example, on the old JIT. So if we support SIMD on x86, it's going to be with the new JIT. It's just not something that's practical to do in the old JIT. We're looking at going from SIMD to more GPU, longer length vectors. So that's something that's just in the we're thinking about it stage. And IL to IL optimizations is also something we'd like to look at in the future. So dynamic optimizations, the sorts of things we want to be able to do is utilize information that's available dynamically, such as types and behaviors that we can then use to do better code generation. In some cases, we can do this without profiling by doing effectively guarded speculative optimizations. And here we can use information that might be invalidated dynamically, or information that is only available, for example, once we've run the static constructor. And another example would be we could defer code generation of anything that's post-dominated by a throw or otherwise predicted to be rare. And because we're in a dynamic environment, we can recover if it actually does happen. But these things could be costly. So these are the sorts of things we'd like to have profiling information to guide. And so the sorts of information that we're looking at, wanting to have available are pieces of information about the class hierarchy, properties of methods. This starts looking a lot like, the things that System C# has specified in the method declarations. We'd also like information about the observed behavior, what the profile looks like, and then again, some static information that is only available after JITting. So we could make, once we've JITted a method, we could make the information that we've observed about that method available for future callers of that method. And we'd like to make further progress on loop cloning, doing multi-versioning, maybe vectorization once we've got the SIMD stuff out there and working. Again, deferring the generation of the alternate loop, which we are currently not doing. Devirtualization, changing interface dispatch to vtable-like dispatch, changing virtual calls into possibly direct calls, and allowing ourselves to actually inline, which is the big benefit there. Generic specialization, optimizing the dictionary lookups that we're generating now. Method cloning. So here again, inlining is extremely valuable, but sometimes we have something that's too big. But it would be nice to be able to take the information that we could have known at the call site and actually incorporate it. So generate a specific method that can make assumptions about types or values of the incoming parameters. And shape equivalence is another thing, especially if we get further on into more interested, more use of technical computing. Once we have things like SIMD, that having shape equivalence information about arrays would be very useful in generating good code. And I think, yep, that's it. So I finished in time for my questions. Anders. So, okay, so Project N is ahead of time compilation of managed code. So, what else can I say about it? Yes, I mean we already have code out there and executing that has been statically compiled. But yeah, we're going to talk about this at build. So. So how this relates to that is that these are currently completely independent, except to the extent that we have a couple of developers who are working on plugging in the new JIT into a Project N environment. So that's the only link today from an actual practical standpoint. But from a prospective standpoint, which is to say, where are we going? Currently, Project N, there are a number of constraints around what you can support because there is no JIT. So the expectation is that in order to enable those features, we will be using the new JIT, plugging it into the Project N runtime. No. So this is all a little bit of speculation, but putting my own personal bias on it. I don't think, I'm not one of those who subscribes to the notion that we should have a single compiler to do all. So my expectation is that in the long run, we will use the existing NUTC, which is the Project N version of the UTC backend. So that will continue to compile IL for pre-compilation purposes. But where you want to do dynamic code generation, for example, you don't want to have to generate every possible generic method instantiation at pre-compile time. You would dynamically JIT. And so, yes, so again, my expectation is that in a scenario where you truly do not want to do any runtime code generation, you wouldn't see RyuJIT. So feel free to jump in, Kevin, if you disagree with me on any of this. The expectation is that they will. It does not today. But word from the UTC team is it would be, I don't know, piece of cake, was that the word that was?
Days of work. Yeah. They already have the types. The JIT 32 has never seen SIMD, it's never seen those registers. So we've had a whole lot of engineering work just to get our compilers to understand the types. UTC's had them as intrinsic since they came out.
Yeah. So for UTC, it's a mapping of, okay, I'm seeing this API coming in. Here's the intrinsic that I've already implemented that, that generates.
Well, it's got to be important for us to intelligently talk about it. A lot of people want to say, oh, Project N is the future and nothing and all this good stuff. I don't personally believe that either, but I think it's really important that we get that.
Yeah, so I'm not sure who we're going to confuse, but I think there's sort of two sides to the confusion, right? I mean, there's one side which is, do we really think, and again, a little, judgment here, personal, lack of objectivity. Do we really think that the future involves no dynamic code generation? I'm pretty sure the answer is no. But then there's the other side of, do we understand the engineering complications of having all of this stuff work together? And the answer to that is, one, I'm really confident that we can get it right. Two, we're working on it. So, Andrews, I think you are in a much better position than I am to make sure that we message that effectively. But I totally agree. I mean, I think that, it is not, I know there's some sort of, for those of you not in the product group, maybe you don't see this, but there's this sort of code generator back-end kind of competition that sometimes seems to be discussed. Personally, I just don't subscribe to that. I think that, the notion that, oh my God, we're the biggest software company in, okay, maybe not the biggest in the world, but, we're pretty darn big, and, so much code executes, and we can only have one compiler backend. It's just, I can't even imagine. But particularly when you look at static compilation versus dynamic compilation, the constraints are so much different. For static compilation, you really want to make sure that you are expending the resources that are available to get the best code. For dynamic code generation, you better make sure that you can run in an envelope that's at execution time. And I think it's very difficult. I have actually gone down this path, in my history. I thought, yeah, we can have one compiler for Itanium, and HP did not have the C++ backend for our Itanium VM. We decided after a while, this is really a bad idea. What we can share is the machine model, but really the constraints are so different that it affects the engineering choices. So I think, certainly from an engineering context, I think we absolutely need to have different ahead of time and JIT time compilation. In terms of how we message the ahead of time compilation versus dynamic compilation, that's to a certain extent out of my hands, except to the extent that I want to make sure that we are there with a JIT that is at least competitive. Right. Yeah, and like I say, right now we are we're actually working on integrating the new JIT in with Project N.
The high-level pivot that I generate here is that full pre-compilation is really focused primarily on devices where you don't want to be paying for JIT, and dynamic code execution on the server side of things. And right now that's kind of binary, and it's clear that needs to be much more analog, where there's some places that you talk to the device where JIT is okay, and there are plenty of places on the server where you start with pre-compilation and you dynamically adapt that.
And the key is, from a technology perspective, the key is having the technology coexist so that those dials can then be applied. And we are working on that.